Hi guys, this is my first video in about a month and a half. I just finished a project I've been working on for the past 2 or 3 weeks that I wanted to make a quick video showcasing. If you watched my last 2 videos, they were on like a large C project I was building for my computer. I got kind of bored of that project, so I decided to put that on the back burner. But one part of the project, which was the first video, was a testing framework I built in C that would run on my computer. I thought it'd be interesting to take that project idea and make a similar project, but instead target my TI-84 graphing calculator. So this video is going to showcase a testing library I made for the TI-84. Anyway, we're going to just step through like a quick demo through the GUI, through what it looks like running the program, and then we're going to write a test of our own. And then at the very end, I thought it'd be cool to actually go into the implementation and see how it works, and specifically how it differs from maybe the testing software that runs on a normal computer. So anyway, let's get into it. Okay, so for the remainder of this video, we are going to be switching between this screen, which is the TI-84 emulator, and this screen, which is the terminal where we are going to be writing code and building the corresponding binaries. As I said before, the first thing we're going to do is just demo the testing program on tests I already have created. So I already have that set up for us right here. It says run unit app, and then we provide in the function call a reference to the test or tests we want to run. In this case, it's multiple tests. It's the tree pane suite. Okay, I've actually already built this binary, so I can just send it to the calculator right away, and we can take a look at what happens. So we're going to send it to RAM, hit program, hit enter. Okay, and here we go. We can see that when we ran the testing program, it prints out this big GUI for us to use. It's pretty intuitive to use. If we hit enter, it will expand these little drop-down menus that correspond to the tests that we gave the program. The blue labels are individual test cases. So for example, the tree pane suite contains another suite called the tree pane node suite, and inside of that suite is a bunch of test cases. So this one's called structure simple 1, there's structure big 1, UD simple 1, I kind of forget what that stands for, but you get the point. Now we can run the test cases individually, or we can run the entire suite at once. To run anything, we just click 9. So we're going to run structure simple 1. Okay, that was fast, but what really happened there was it rendered a whole new page just for the structure simple 1's output, and then once the test ended, it came back to this menu. Because the label is now rendered in green, we know that it completed successfully. If we want to later go back and look at what messages were logged during the test running, we can hit 6, and it'll show the log of messages. It happens that this test, and actually all the tests in this beginning demo, actually don't print anything out because they succeed. So this is just an empty window. Now, we don't need to, as I kind of alluded to earlier, we don't need to run each test one at a time. Let's say I want to run the entire tree pane node suite at once. I can click 9 on its label, and it'll run all the tests. Once again, all of these tests succeed. And that's basically the gist of the whole project. The other thing to note is that the output of each test is saved in memory, and anyone who has coded on the TI-84 knows that it doesn't really have that much memory at its disposal. So maybe you have hundreds of tests, for example, if you run all of the tests at once, the calculator might actually run out of memory, which wouldn't really be an error. It would just, you're just giving the calculator more work than it can handle at a given time. To get around this, for example, we ran the tree pane node suite, so the output of all the test cases are saved, and that's why they're all green, saying that there's success. If there was a failure, it'd be red. If it was a warning, it'd be yellow. But moral of the story is that these tests ran, and you can view their output. If we want to delete the output to free up space to maybe run other tests, we can actually hit 3. And this will bring all of our tests back to this blue state, which signifies that they haven't been run, and there's no saved state in memory. Anyway, that's kind of the gist of this beginning part of the demo. Again, if you forgot anything I just said, any of the controls, as it says on the top of the pane, you can always press 0 for help, and it'll walk you through everything I just said. How to navigate, how to run a test case, how to delete logs, and how to exit. So yeah. Okay, so now let's see what goes into actually creating a custom test of our own. To do this, we are going to look at the unit.h header file. It should be noted that all of the modular library code used in this project resides in this single self-contained directory cxx util. So anyway, let's check out unit.h. This header file defines all the necessary structures to run the core part of the testing software. It doesn't really deal with any of the GUI stuff, just the very basic, what is a test, how to run a test, how a test should be structured. With that, we can see that the header file provides a template for creating a test. So we are going to copy and paste this into our main.cpp file. Okay, so a few things to note here. This is just the most basic template. You don't need to follow this structure to make a test, but I feel like if you have one standalone unique test, this is probably the best way, which is that we have one static instance of the test, and then we expose a pointer to the test, which then you can pass into run unit app. It should be noted that in the constructor of the test, you really shouldn't do anything. When the test runs, it should set itself up and also clean itself up all in one go. If you do run code in the constructor, it will run when the test case itself is initialized, which isn't necessarily when you click 9 to execute, for example. But anyway, now we can get into actually how to implement these attempt and finally methods. So attempt should really hold the core of your test. It should set up the data that you might be testing, and it should run assertions depending on what information you get back. This is all based around this function here, or not this function, I'm sorry, this parameter that's given, which is a test context. This is kind of similarly named to my earlier testing video, but a little bit different. So we can see that if we have our test context and we see what it provides us, we get all sorts of methods. We get assertions, we get simple logging, info or fatal. We also get labeled assertions, and we can kind of see what's going on here. So for example, let's do the most simple thing we can do, which is just print something. So we'll do tc info, hello from my test. And we don't need to do anything in finally because we did not allocate any memory. And if we want to run this, we can simply go in here and we can just pass in my test case only. Now let's see what happens. We rebuild our binary. Takes a second. Then we can come back to the emulator. Oh, that's wrong. Send it our new binary. Run it. Now we can see we no longer have the tree pane sweep, but we just have one test, my test, the one we just created. And if we run it, we see it's successful. And again, we can hit 6 to look at the test log. And in the test log, we have hello for my test. Cool. Now let's say we wanted our test to actually do something, like maybe an assertion or something. This is pretty simple. We can do TC. We get all sorts of calls. I think the most useful ones are like the label assertions. This way we can differentiate between different assertions in our call. So for example, we could do, let's do label assert character. And we're gonna say assertion 1, and the expected is gonna be A, and let's say we actually get out B. So this should fail. Make. Give me a second. Okay. So now let's run our test. Hit enter. So now we have my test again. We hit 9, and now our test comes in red, signifying something went wrong. If we look at our log, we can see at the label assertion 1, there was an assert equal character failure. The expected was A, but the actual was B. So that's kind of helpful. So anyway, besides the attempt method, each test also comes with this method, the finally method, which is really extremely important, especially in C++, where there is no garbage collector. So just to remind you, in C++, if I have a pointer to an integer, for example, actually, let's do it like this. Let's say I have a class. I'll say my object, and it holds a singular int. Now, to create an instance of my object in dynamic memory, I'm going to use the new keyword. So it looks something like this. My object, obj, is going to equal new my object. Very simple. Now let's say in my attempt function, at the very end, because this is C++ and there's no garbage collector, I need to delete my object like this. This is essential to prevent a memory leak in the test, right? Remember, on this calculator, memory is sparse, so even the smallest of memory leaks could crash the program. So this looks fine and good, but the problem is that this is a test, right? It's not really expected to succeed technically, right? For the whole test program to run correctly, it doesn't necessarily mean that each test individually succeeds, right? It needs to be equipped for when a test fails an assertion, for example. So that would look something like this. Maybe I have test context fatal, and there's some fatal error, not very good, right? The problem here is that the test does not continue execution past this line, past line 32. So this line never runs. And this obviously is a huge error, right? To get around this, I added this finally method. And the idea here is that if you're going to create pointers to dynamic memory, which are going to last for the duration of the test, you should really delete them in this finally block to prevent, unwanted memory leaks. So to do that, we would do something like this. We would make the pointer just a field in the class, instead of just a local variable in the function. And then instead of deleting it at the end of attempt, we're going to go into finally and do delete this.obj. So there we go. Of course, no one is perfect, and especially in C and C++, it is extremely easy to forget to delete dynamic memory, or maybe not even realize that you allocated dynamic memory, and maybe there is a memory leak, but it just, it slipped through your hands, right? Luckily for us, my library provides a simple, very simple support for checking for memory leaks. It's not the most rigorous system, but it's actually identical to the system in my original testing video, just modified to work in C++. So again, let's say we don't have this line, we don't have this delete object, and we build our test. It's taking a second to link. Okay. Here we can run our software, and it says there's a fatal error, which is what we told it to print out. But there's really no mention of a memory leak, which is what went wrong. So maybe, for example, we had an assertion error or we had no error at all, but regardless, there's a memory leak. We would like some sort of notice so we can look over our program again just to make sure we catch that leak. To do that, it's actually extremely simple. We really just go up to our myObject class and we make it extend something called a safe object. There's also a safe array, which is kind of the same thing, but we'll just go over safe object for now. There is a default constructor for saved object. There's also a okay, there's one that accepts a parameter, but that's actually not really that important for this video. So anyway, now, let's say we do the exact same thing. We make our program. Taking a little bit to link. Okay. Oh. Okay, now let's run our test. My test. Now if we look at the log, we actually get memory issue. See, what happens here is that our safe object actually overrides the default new operator. So that when we create a new myObject, which is really a safe object at its base, it'll increment a little number somewhere. And then the fact that we didn't delete it, the testing library can check to see if the numbers at the beginning of our test match the numbers at the end of our test. In this case, they don't. One number is probably one higher because we created one object and did not delete it, and we can register this memory error, right? Okay, I wanted to just point out a few more quirks about working with the library. One question you might have is what types of strings can we pass into assertions and log statements? For example, let's say we had a string called message, and we create this string inside the attempt stack frame. So we know that message will no longer exist after attempt returns. Can we still log it in this way? What will happen, right? The answer is yes. You can still log it like this. The way the test context works is that whenever you pass it a string, the string is copied into a new section of dynamic memory. So even after your test returns, copies of the strings you gave it will exist in the corresponding output logs. The last quirk I wanted to point out was you might be thinking to yourself that this is a very verbose way to define a test, and I would agree with you. It'd be really annoying if you had 40 tests that all essentially do the same thing, but maybe have different inputs. But you have to have a separate class for each one. That would be, not the most organized approach, right? And also just generally confusing. To get around this, the nice part is that your test case is a class, so you can extend it, and you don't need to make the constructor private. And we can see how this type of strategy would help us in tests I have written for other parts of this project. For example, one part of the GUI is this structure called a text block. Let's go into here instead. And we can see that I make this class a text block test case, which is actually not specific to any singular test. It kind of just sets up the steps we're going to take for any test that we make to test the text block. So what I mean by that is it comes with an overridden attempt function, which does all these assertions and calls the text block in a certain way. Comes with the finally block overridden. But the constructor is exposed to the public, and there is where you give it the input and the expected outputs. So now, instead of having a different class every time we want to test our text block in this way, we can just create static instances of this text block test case class, right? So here, we have all these different tests, and they all look pretty similar except for the inputs, right? Still a little bit verbose, but much better than the alternative. Okay, so for the final part of this video, I wanted to talk about the implementation of the testing library at its core. I will say as a disclaimer, the majority of this project's code was the GUI. And the GUI is actually completely independent to the testing software. When I was in the main file and I did unit app.run, unit app is kind of like a whole specific application that ties together the unit library and the GUI library. A unit test itself is completely independent of the GUI, and you can run it however you want. However, at its most atomic form, it runs in a specific way, which we're going to talk about now. Basically, before I get into this, I just wanted to say, like, my previous testing framework I wrote to run on my computer took advantage of the notion of processes, right? I could take a test and run it on a separate process. And this was really nice because if the test did something catastrophic and the process crashes, the testing parent process can persist and actually report that catastrophic failure. This is not the case with this testing software. The TI operating system is much simpler, and I am maybe a little bit less versed in it, so I couldn't really find a way to salvage the program if the test does something very illegal. If the test does do something extremely illegal, like, I don't know, write over the operating system, for example, the RAM of the calculator will clear itself, kind of as like a defense mechanism. That's not something I implemented, that's something that just the calculator does innately. But anyway, this all being said, the structure of how my tests run is much different than the structures of how they run in my testing framework I made in C and in maybe a normal testing framework you would use on your computer. Most specifically, where a normal testing framework might use the fork call to create a new process, this uses setJump. This is kind of an interesting function in the sense that it has a similar behavior to fork. Fork is known to be called once and return twice, which means that you call it once, but it'll return at the same line in the parent process and also return at the same line in the spawned child process. setJump also technically returns twice, although in a different way. So the way setJump works is that when you call it for the first time, it saves the state of the machine in this environment variable. And then what happens is that when you call longjump later, it'll go back to this line of code and reset all the register values to exactly what they were when you called setJump. It's really nice for error handling, because now when I attempt my test, I don't need to implement some sort of weird macro or something to return in some special way. I can just call long jump no matter how deep I am in the stack, and it'll always return us to line 36. So that's basically how this works. The test context, if you do like a fatal error or failed assertion, it'll call long jump after logging some sort of messages. Then that'll bring us up back to line 36, and exited will take on a new value. Given that exit is non-zero, which in this case it won't be, it'll skip over the if statement that ran the test initially, and it can finally continue to the namesake finally method and finish up our test. The last thing I wanted to note also is that this is actually designed a little bit better than I had designed it in C for my computer, which is that I provide this thing called a test monitor. And this is interesting because it's kind of like, I guess, a visitor maybe. Maybe I'm using that term wrong, but the idea here is that you might want to display the output of your test in many different ways, and you don't want the test itself to really be linked to the way it's outputted, because those are kind of different pieces of software. So the idea here is the test monitor actually provides a function for logging. So when you log, for example, a fatal error or a failed assertion, instead of doing a very specific action, it actually will call the log function of the test monitor. The test monitor is an abstract class, so it's up to you to implement it however you want. Maybe you want the log just to print to normal TI output. Maybe you want the log to do what mine does and stores it somewhere in dynamic memory to be read later, right? It's up to you. And this principle allowed the unit library to be completely independent of the GUI, which I thought was pretty cool. Anyway, that's basically it for this video. If you made it this far, thanks for watching. And I hope you enjoyed. And I'll be sure to have a new video soon. Thanks.